Okay, so it's slope going up here, smooth pulley at the top, down there, angles, both these angles 30 degrees, and I've got P there, so that's the P side, and this is the Q side, and they're joined together, and that's M is here, and at M there's friction after here, but there's not friction before. It's smooth up until M, and there we are, drawing them up here. Smooth pulley at the top, and the smooth pulley, the reason that's important, it means the tensions either side are the same. First thing, I'll put the forces on here, the weight going straight down, and this one's 0.3 G, and I've got a normal contact force R, and I've got tension, and tension string must pull up, and it's smooth between A and B. A's here, B's here, smooth all the way up. Actually, it's smooth from B until M, so there's no friction. I've got a smooth pulley, so I've got equal and opposite tension going the other way here. I've got this one here, it's a bit heavier, it's 0.4 G. I've got R, it's obviously a different R to the previous one. And I've also got an acceleration. The string is inextensible, so the acceleration here must equal the acceleration going down there. And now it tells me to find the acceleration, it's 0.7, and find the tension. So I'm certainly going to have to resolve it, and I'll do the left hand side here. So resolve, and I'll resolve up the slope, and because I've got an acceleration, resultant force equals mass times acceleration. What's going up? I've got T, but I've also got, if I think about my force here, I've got this component of the slope of the weight coming down, and that's 30 degrees there, so that's 30 there, so that's T, and this is minus 0.3 G, and that'll be sine 30 equals the mass, which is 0.3 times by the acceleration. And this side here, I'm going to resolve down the slope, and again I'm going to get resultant force equals mass times acceleration. And here I get 0.4 G, and this will be sine 30, take away T equals 0.4 A, and those are my two equations. And if I add them together, then the minus T and the plus T will disappear. So I'm going to add those two equations, and that will give me 0.3 G, 0.1 G, 0.1 G sine theta equals 0.7 A, and that works out that A equals 0.7, and now I need a sub into equation 1, and substitute into equation 1. If I call that equation 1, that gives me T minus 0.3 0.3 G sine 30 equals mass times acceleration 0.3 times by 0.7 the acceleration, and that gives me a T equals 1.68 newtons. That's the first part. Q reaches M 1.8 seconds after being released from rest. So I'll do it here. It's got constant acceleration. I just worked out the acceleration is 0.7, and so I'm going to set up, I'm going to do a Stuver equations, which are actually the equations for constant acceleration, which is what we've got here. So we know the acceleration is 0.7. It tells me that the time 1.8 seconds. The initial velocity is from rest, and so I can work out what the final velocity is. I don't care about S. So I got this V equals U plus AT. So V equals 0 plus 1.8 times by 0.7, or the other way around, but anyhow, V equals 1.26 meters per second. So I've done that bit. After Q passes through M, the string remains taut and particles decelerate uniformly, and Q comes to rest between M and C. So it comes between M and C 1.4 seconds after going through m, so 1.4 seconds, that gap there, and then v will equal 0. So again, I've got constant acceleration, so I'll try and do it here. Constant acceleration, so I can use Stuva, and I've got time 1.4. The initial velocity is the velocity which I've just worked out, the speed when it reaches m, so u will be 1.26. Final velocity is 0, and the acceleration is what I want to find. Don't care about that. And so I've got v equals u plus at again. V equals u plus at. So 0 equals 1.26 plus 1.4a. So a equals, that will work out, minus 0.9 meters per second squared, and therefore the deceleration is 0.9 meters per second squared. So I've done that bit, and 4 I'm going to do it in different colours so I can try and get it all to fit on here. Find deceleration, done that bit. By considering the motion of P, find the tension in the string while Q is moving from M towards C. So I'm now going to just consider the P bit over here, and I'm going to have to do it here for part A, and to resolve up the slope like so, and I'm going to have resultant force equals mass times acceleration. What have I got going that way? I've got T going up minus 0.3 g sine 30, and I've got no other forces, and that will equal the mass, which is 0.3 times by acceleration minus 0.9, and that works out that T equals 1.2 newtons. And then finally B, calculate the magnitude of the frictional force which acts on Q while it's moving. So there's actually now, I'll do it in red, there's now a friction force as it goes beyond here, and so I can use that formula. So for B, just like that, I'm going to now resolve down the slope, and I'm going to have resultant force equals mass times acceleration. And the resultant force, I've got this component here of the weights, so I've got 0.4 g sine 30 minus, I've got a tension, just worked out tension 1.2, and I've got friction also going up the slope, so minus F equals my mass, which is 0.4 times by negative 0.9, because that's the acceleration. And if I work that one out, that comes to F equals 1.12 newtons. And it's quite a long question, but actually, if you take it in bits, it's okay. You might have wanted to draw another diagram for this one here. I just added it to my one up there. But that's question 7 and the whole paper done.